on the nice meeting logo, it's supposed to tell me when I get questions, and it was 0 for the whole time, but I just learned there was a slew of them. And so I looked at them. One of them was the volume numbers. There's no volume number on the cover of the books, but if you look in the inside of the book, there's a volume number. So if you want to try to keep track. The other one was about what causes field line currents. How do you get a current to flow along a field line? And there's if you go back, you can think of it a couple of ways. One is if you have there's a chicken and egg issue with Ampere's law, curl B equals J. Does it say that if I have a curl of B, I have a J, or if I have a J, does that mean I have a curl of B? Right? It's equivalent. And so you can say anytime I have a curl of B, it means I have a current. And so if I twist or bend a field line, I'm going to have a current. So you get field line currents naturally. You could also think of it in terms of the plasma dynamics. If I can accelerate particles along a field line, I usually are going to have a different velocity between the ions and electrons for the same energy. An electron is so much lighter, it's going to stream away, right? So I can get a different flow. So if I can have a potential drop along a field line, I can accelerate particles. And I'm going to be with a potential drop, I'm accelerating particles in the other direction. So I get this big velocity difference. So, and then the third question was, often in physics, we develop heuristics, or essentially a theoretical construct that we know that's not real, but is very useful. And one of the problems in physics is we often have these, and we're not sure. So gravity. What's gravity? We know it's there, and I have these, I can draw potential lines, but is it there? Or with reconnection, it's there, is that there's a process that we know that converts magnetic energy into particle kinetic energy. So it's, there's debates on, are there flux tubes? Are there field lines? Is field line a misconception? I mean, do you see the field lines in this room? How would I see them? I could measure them. I could put a compass out here, right? And if a dip meter, I would see it bent there. Or if I could evacuate this room and fire an electron beam and let it glow, I would see the dynamic, right? I mean, so I can see the field lines, but I have to do something. You know, it's like, do I see gravity? I can drop something, and I could then do it. So, but reconnection is a little bit different in that it's not a nebulous construct. It's more of a physical process. Okay, I'm going to shift to iPad and see if this works. And we're going to start with a quick poll, and this is a yes or no poll. And when I hit this button, it should appear on your screen. I'm hopeful. And did anything happen? How about now? Okay. So do you guys hit submit? So everybody hit submit. And then it should. And then okay. So anybody want, is there one scale? Is there one scale relevant for heliophysics? Actually, there is. But it depends on who you ask. Right? And so everyone, regardless of what area you're going into, you're going to have typical time and length scales in your head. And a great way of finding out what type of physics somebody does is ask them, what type of scales do you work in? Oh, I deal in nanometers. Oh, you're doing, atomic stuff, or megaparsecs. Oh, you're an extragalactic astronomer, right? I mean, you start thinking about things. A planetary person will think in AU, magnetosphere, and Earth radii, right? And so that's the cool thing about scale and length scales, is that we create our own by dividing one number by another, and we get a dimensionless number. And so whenever you have a big number, it's just divided by itself and you got a new unit. Or a really small number, right? I mean, and so then we give it a name. And so plasma physics is filled with these dimensionless parameters that tell you something about the physics, either the length scale, the Reynolds number, or whatever, right? It tells you about what term on the right-hand side of the force equation is important, because all those dimensionless units are the ratio of one force term to another force term. And so you say, oh, the Coriolis term must be important, right? So the scale that's relevant depends on the problem you're looking at. And there's lots of scales. And you can always tell a theoretician because they don't work in real units of SI, of meters. They always have some type of skin depth, or units of, of omega CI or whatnot. But we're going to start going through some of these scales. So just like I started the last one, if you just want to try to remember what the theme is, we're going to look at scales. So when we talk about flux tubes, current sheets, and cavities, are there any natural scale sizes? Or what determines the scale? Why is the magnetosphere the size it is of the Earth? When I draw a flux tube, what determined that 80 light-year long flux tube in the center of the Milky Way galaxy? Why wasn't it 40? Why wasn't it something coronal mass ejection size that we would no way be able to image a couple tens of thousands of light years away? And the good news is there is a small set of plasma scale sizes that order all the physics. There's tons of them. There's a zoo, and there's an NRL book that if you email NRL, they send it to you for free. It's a fundamental plasma parameters, and it has just tables of everything and conversions, and very handy dandy. I guess now you can just Google everything, and it won't even have to return your result. It'll just tell you what the scale size is. But if you can figure out what the important scale size is for your problem and keep them in the back of your mind, that allows you to solve problems really quickly. Because often we have really good ideas, but if we just thought about it for a second, we realize how stupid that idea was. And you don't know how stupid it is if you don't have the scales right. It seems reasonable, but when you actually figure it out, nope, not reasonable. And then the other point, and what you'll hear about after the introductions, is reconnection. In reconnection, let's see if I can do this, yeah. So reconnection is a cross-scale process, in that you have scales that are important for reconnection. The small scales determine the physics of the reconnection across the current sheet, but what determines the rate of reconnection or the structure of reconnection or what happens is the global scale, and how the small scale can change the topology of the field line, which impacts the global scale, and how that global scale impacts the rate of reconnection. So you have this coupled, two-way coupling between the scales, and so it makes it a little bit more difficult. So the heliospheres in the news yesterday, IBEX released results looking at the neutral atoms, instead of coming from the nose of the heliosphere where the big press was the ribbon, was that there seems to be structure to the interstellar medium in terms of the magnetic field orientation. They looked, or bend all the data looking downtail. What does the magnetotail of the heliosphere, or the heliotail, look like? It actually is this four-leaf clover pattern of high fluxes with high-speed flows and low-speed flows. So it's kind of interesting. And if you're an astrophysicist looking at stellar heliospheres, you can see all different types of complicated tails. And so it's not too surprising that the Earth's, or the solar system's tail is also complicated. And hopefully, within days, maybe it has already happened, these guys cross over into interstellar medium, the Voyager spacecraft. And there was another interesting results released this year. 3 instruments that are returning data from the Voyagers. They were launched back in the 70s, are streaming out at 120 AU or so. And they're measuring cosmic ray flux, the solar wind plasma, and magnetic field. And the prediction of what should happen when you pass over the plasma pause is you're going from one cavity, so one plasma domain, to another plasma domain. So what does the sun's plasma a magnetic field do to the surrounding interstellar medium? Right? It pushes out, it forms this cavity, and you would expect there should be interstellar stuff outside and solar stuff inside. And so you're looking for changes in the cosmic ray flux. So cosmic rays are coming in and some generated at shocks. You're also looking at change in the behavior of the magnetic field from the IMF that's really weak out there to whatever the interstellar medium field is. And what's interesting is the cosmic ray flux in the plasma regime has changed, but not the magnetic field. So did we cross it? So there's a bunch of ideas that have already percolated out. And one is that we're essentially going through the current sheet, that Chapman-Ferraro current sheet that has some thickness. And so you can imagine that there are interstellar field lines going in one direction and solar field lines going in another, and you get reconnection. So I have connection to the interstellar medium plasma. I'm on a flux tube that had one end in the interstellar, but the configuration of the field hasn't changed. I'm still in this current sheet. So maybe we'll actually pass through. When we draw this picture of the sun now, and all these little circles are the orbits of the planets. There's a termination shock when the supersonic solar wind slows down. Then there's this sheath region before the heliopause, and then you're out into the interstellar medium. So this is the main cavity of heliophysics. It is the domain of heliophysics. Everything inside this domain is relevant to heliophysics and has discussions. But we span our solar system because we're not the only star in the universe. And we have the ability to observe other heliospheres, or what they've termed astrospheres. And so here's a star in Orion, and looking at which direction is this star moving with respect to its interstellar background. You can sort of see the pushed in magnetosphere, heliosphere, and then this very long tail and complicated stuff going on down here, little bits of matter. So there's these huge scale sizes from astropheres and heliospheres down to magnetospheres. Fran Wagenhall is going to give lectures on planetary magnetospheres, and essentially everything is magnetized, even those that aren't. So Venus and Mars have no intrinsic magnetic field, but Venus has a very dense atmosphere that gets ionized by the ultraviolet of the sun, and then it starts flowing, and once you have moving charged plasma, you get currents, or you induce a magnetic field, and so you have this induced magnetosphere, forms a tail, and there's flux ropes and all types of things in the Venus ionosphere. Mars has remnant crustal magnetic fields, so part of the surface still has magnetized rock that can extend out into the Mars thermosphere, ionosphere, and so you start getting mini magnetospheres depending on where you are in the Martian atmosphere. And then all of the outer planets have magnetospheres. We have Messenger at orbiting Mercury right now, and it has a very nice compact magnetosphere that has this dipolar configuration. It's at 0.3 AU or so, and so if you scale all of the solar wind parameters, you can figure out what is the solar wind dynamic pressure at Mercury, what is the Elfing velocity of the solar wind at Mercury. So you can just scale it, and the dimensions of that magnetosphere make sense with respect to all the plasma scales due to this higher density, higher field strength regime. As you move out, you head to the Earth, and you can see that that circle in there is the size of the Mercury magnetosphere. So the Mercury magnetosphere is teeny compared to Earth. So the field is smaller, and then the background thing that confines it is stronger. And then as you move out to Jupiter, you can see where the Earth's magnetosphere would sit. In almost all of these pictures, we draw with the sun on the left and the magnetotails cut off at some arbitrary distance. What determines the length of the magnetotail? So with ibex, I'm looking down this helio tail. How far does that go? Is this astrosphere? How far does a star's plasma and magnetic field go? Yep, so you can just use your conservation laws. I have this much stuff coming from the star or the planet, this much magnetic field. When does it go away? Or when does it merge into the background? And so the Earth's magnetic tail was crossed actually by the Voyagers on its way out at a couple thousand RE downtail. It passed through a regime where you saw a nice sort of lobe signature crossing a current sheet. So you can imagine that the plasmoid flux ropes that are ejected due to reconnection, they have to go somewhere. And if we're aligned with Mars, we have a Earth plasmoid flux rope interaction with the Mars crustal field or whatever, right? So, and then as you go to the outer planets, we have Cassini still in orbit around Saturn. And you have now the scale is going down, the Earth scale is in there. Why does Saturn have a really big magnetosphere? There's two possibilities. Why is it big? So it has its own big internal source of material and magnetic field. Why else? So rings are a source of a lot of it's a water-dominated plasma, which is kind of wild because a lot of the water dust grains get charged. And so you have a mass ratio that's opposite of what you normally think of proton-ion electron mass ratios. The negative ions of Saturn take the role of the electrons. So they're these dusty plasma-dominated Saturnian, really cool. And you're going to hear about dusty plasmas later next week as well. But why else? So I can have I could be Hercules, and I'm strong and big, but what would be another way of getting it big? What if it was weak? Could I have a big magnetosphere if I had a really small intrinsic magnetic field and little plasma? What determines that boundary? Sure, it's a pressure balance. Whatever I'm pushing out is balanced by inside, right? So how big is the balloon? If I'm at high altitude, my balloon's going to be really big, if any of you have done weather balloons, because the background pressure drops out. It's not that I'm adding helium to my balloon, it's just that my external pressure is weakening. So when you're at 10 astronomical units away, what is the solar wind density? How does solar wind density fall off from a spherically, right? So 100 times weaker than Earth, right? How about the magnetic field? So, it's almost all azimuthal component. How does the azimuthal component of the IMF, run over R, right? It's falling off. So it gets really weak, the pressure, so you get a big field. So those are determining the scale sizes. One of the cool things about planetary magnetospheres is that we now have discovered that there are satellite magnetospheres. Ganymede, one of the Galilean moons, has an intrinsic magnetic field. And so it's a magnetic field that's embedded in the Jovian magnetosphere. So you have the Ganymede magnetosphere in the Jovian magnetosphere, but now it's orbiting Jupiter. So the preferential direction of this dynamic pressure is its motion, and then the co-rotation motion of the plasma of Jupiter. And so it's going around, and of course Jupiter's orbiting the sun inside the heliosphere. So we have these three different magnetospheres, the heliosphere, magnetosphere, and of Jupiter, and the magnetosphere of Ganymede all together. So if I was interested in the dynamics of the Ganymede magnetosphere, would I worry about the solar wind in the IMF? Would I worry about the sun? And perhaps if I have dynamics in the Jovian magnetosphere that could change the co-rotation velocity, I would then change it. So you can get all different types of things. Okay, this image was from NASA. Goddard Space Flight Center has a really cool visualization lab, and it essentially has Pixar people to do data visualization. So if you're working with a NASA mission and you have a really cool idea on a visualization or animation, there is a group at Goddard that can work with you, and they have all of the 3D animation tools and expertise to get your next press release really spiffy. But they made this, but they had them take the labels off of it. What is it? Is it a astrosphere of an extrasolar planet that Kepler discovered? Is it a planetary magnetosphere? If it is, which one? Okay. Sure. But this is any arbitrary one. You could grab this and label it any way you want, right? And nobody would know the difference. There's a cavity, a magnetosphere, a heliosphere has an intrinsic shape because there's almost always relative motion between it and its surroundings. So you have this bullet-shaped magnetotail pattern, and then you have a more rounded front. So this is an astrosphere to an astrophysicist. It's a magnetosphere to a magnetosphere physicist, right? But there's something scale invariant. I could label this. I could say magnetopause, magnetotail, flux tube, right? We call this inner whatever it is. And so when you think about going from one region to another, from one magnetosphere to another, what we often do, we'll put Earth labels on everything. And almost all of planetary science is a comparative. How does it differ from Earth? Why is there an ozone layer in the Earth's atmosphere, and what's going on in Mars or Venus, right, or Pluto as we head out to Pluto? Okay, so think big picture conceptual in your mind, and you can start labeling things, and you don't even need to know what it is. And then you can then start thinking, what are the processes that give rise to the shape? Relative motion, pressure balance. So if you want me to determine where the magnetopause is, just tell me the pressure inside and the pressure outside, and I'll tell you where it is. I want to know how dynamic it can get. What's the range of solar wind dynamic pressure? Or if I'm looking long term, the Earth's magnetic field is weakening. The dipole moment is falling off at many tens of nanotesla a year, right? So you can extrapolate, and within less than 1,000 years, we're not going to have a magnetosphere. The higher order moments are going up, not as fast as the dipole going down, so the aurora are going to be really cool. We're going to have aurora everywhere, right? We're going to have poles all over the place. But what if I wanted to model that? What would be that boundary? Would the solar wind then be able to hit the ionosphere directly? Will it ever get down to 300 or 1,000 kilometers? How would I, right? All the processes are the same. And you can do that for any of the physics. Is anybody doing a thesis that's time invariant? So all the terms on the left-hand side of your continuity and momentum equations, you set the d by dt is equal to 0. Anybody doing any equilibrium? That's boring, right? You need to know it. Who cares, you know? It's like living in Southern California being a meteorologist, right? It's boring. And when something strange happens, that's when you get excited. And so that's why we like disasters. Something big happened out of the blue. It's unexpected. A lot of energy was dumped somewhere. We had a hurricane, we had a tornado, we had an earthquake, we had an asteroid hit Russia. And that was one of the most popular Twitterverse things ever, right? I mean, we like that type of stuff. There's a train explosion in Quebec, you know, a crash at SFO. Those are the things, they're out of the normal. They're not in equilibrium. There's something unusual happened. So we want to study it. So there's whole teams of people who are studying what went wrong. Why didn't the brakeman put the brake on? Or what pilot error or mechanical error was there? What went wrong? So that's what we do. Or we look at, I'm a physician. I want to know how a normal body works, but I usually don't see you unless something's out of whack. Then I have to figure out what's out of whack, what's the cause of that out of whack, right? So in space physics, it's nothing different. We're looking at how do we get away from the equilibrium? What are the dynamics? And for us, we're looking at these coupling processes. How do we get energy from one domain to another domain? How do we get mass from one domain to another domain? How does momentum propagate through the system? And so when you think about your continuity equation, which is worried about mass, right, there's dn dt or d rho dt. How does density change with time? So I'm measuring it somewhere. The cool thing, there's only 3 ways I can change density with respect to time from somewhere. Transport, source, and loss. Right? That's my continuity equation. So if I see it changed, I just have to figure out which one is important. Did stuff come in or go out? Am I creating something? Maybe ionization, maybe a solar flare went off. I ionize the atmosphere and suddenly I see a big increase in my F region density or whatnot, right? Or did I change the chemistry? Did I lift the F region up? And so I have an atomic to molecular ratio that's different and the recombination rate changes, right? I mean, so those are what you do. The momentum equation. You have your dV/dt. So what if things aren't moving? Kind of boring. So I want things to move. So hydrostatic equilibrium says, I'm not going to have vertical velocities. What if I relax that, allow vertical velocities? How do I get stuff out of the ionosphere into the magnetosphere? How do I get stuff from the heliosphere into the magnetosphere? So that's essentially what we do, is we are looking at mass, momentum, and energy transfer through the system. How does a coronal mass ejection drive an auroral storm? How does it make the radiation environment enhanced so an airline pilot is going to get an enhanced dose of radiation? Right? I mean, so that's what we're going to do. And as I had mentioned before, this guy is at the heart of almost all of that transfer. How do you get stored magnetic energy to release explosively? And this MMS cartoon with the 4 spacecraft, from this picture, could you tell me what the separation is of the MMS mission? How far apart would you want the spacecraft if you're trying to actually observe reconnection, where the actual field is going away and you start having the flows? What would you need to know? The scale of what? So you could figure out, what is that pink? What determines that scale, right? What is the blue? Okay, so I'm going to think of scale sizes at the kinetic levels, and when I think of kinetics, I'm thinking of particles. So what are typical scale sizes, kinetics? An electron or ion scale size? So the gyro radius, right? So there's a preferred motion of all charged particles going around a magnetic field. What does that depend on? So your mass, magnetic field. So for gyro orbit, what do you got? You got, how about if I'm a high charge state oxygen atom compared to a proton? They have different masses and different Qs, right? So they're the fundamental parameters that when you think of a particle, a baseball, a football, or whatever, how fast it's going, how big it's going, right? And for charged particles, what's its charge state? And all of those coupled into a magnetic field start giving you scale sizes. And where you start getting some complications is when you start worrying about collisions. Because if I have a collision, then I'm not going to go all the way around, and I'm going to have some other scale size due to its motion, due to sort of its random walk, its mean free path type of thing. And so as you go from the ionosphere, atmosphere, where collisions are important, to the collisionless plasma of the magnetosphere and heliosphere, you can think about different scale sizes. So as I mentioned, the magnetospheres are self-similar. And this question of what are the scales of magnetic reconnection? And you hit on them. Essentially, this sort of hierarchical scales, what would be the smallest scale in a plasma that you could think of? It doesn't have to be the exact one, but I've already mentioned electron scale, right? And I can think of all different types of electron scales. If I'm an atomic spectroscopist, I might actually be thinking about collision cross-section between an ion and an electron type of thing. And so then you start bringing in those types of scales. You can think about the gyro radii. There's a bunch of scales that you can think of, but those are the ones that are important for the reconnection. But that pink is embedded in a macroscopic magnetotail. So what's important for this magnetotail? What would be a scale size that's important at the large scale? What determines the flows of the Dungy flux tubes going over the polar cap and forming the lobes and the plasma sheet? So, okay. So, what was the first, the simplest form of the plasma equations? If you take your continuity, mass, momentum, energy equations and simplify them, that's often where we start, but not always. Chapter 2 of Kivelson and Russell, or chapter 10 of Jackson. Ion scales, collision MHD scales, right? So this big scale is when you have all your invariants, all your motions are conserved. So there's 3 fundamental scales in a magnetosphere. You have your gyro motion, which we already talked about, and that is associated with the first adiabatic invariant. Then you have a bounce motion, and then you have a drift motion. And at the scale where those are invariant or they're conserved, life is easy, right? Because then we can do a lot of simplification. So this large MHD scale. So we're going from that large, slow, long time, big scales all the way down to electron scales when you're worried about reconnection, because those big scales determine where that current sheet is, determine what the magnitude of the lobe field is, which determines the magnetic pressure, determines how much mass flux is coming out of the ionosphere to weight up the mantle and what the density of the plasma sheet is and all that, right? So reconnection is this cross-scale coupling, and that's one of the reasons why it's so difficult. Tom Moore wrote a paper, review recently, looking at the scale size of reconnection, and here's putting some numbers on it, but if you don't want numbers, because they would potentially change depending on what type of plasma regime you're in and where you are. But essentially, you can recognize the magnetopause here, where you're going from one cavity, say the Earth's magnetosphere, to the other cavity, the heliosphere, and we have a reconnection going on at the magnetopause. If we wanted to actually understand that physics, we're going to be going down into this current sheet scale, so where the ions and electrons are magnetized, so they're still moving with the magnetic field. And then we get into a regime where the scale is such that the electrons are no longer bound by the magnetosphere. They've been decoupled. And so we are going from these hundreds of thousands of kilometers down to 100 kilometers. So if that's the case, how far apart should I make MMS? Yeah, so 10 to 100 kilometers. I want to get down into the electron scale. It does, but you fly big fuel tanks and you correct it as they go around. They're in a large orbit, and there's a really cool idea that NASA doesn't have any money for, and there's a letter from the community for Themis, which is a NASA mission with 5 spacecraft, and there's 3 inner probes that are trying to develop what's called a Crossscale concept. The 3 Themis probes have enough fuel that they can form a tetrahedron around MMS, but at the MHD scale. So you can go have 1,000 kilometer type of separation between Themis and the MMS. And then MMS is down at this 10 kilometer scale. So you would, because that's one of the problems with MMS when you're thinking about it. If I have really good electron scale observations, I have no idea what's going on around me. So I see the dynamics. I'm not sure really what the global dynamics are. So I'm going to have to run models to try to figure it out. And I'd love to have some validation of those models. But the Europeans proposed Crossscale in the last European competition. It's €1 billion type of investment, and it wasn't funded. And I think it's $900K that NASA needs to come up with to get this Themis, but with the current budget, it doesn't look like it's going to happen, which means it probably won't happen in our lifetime. Okay, so what are some of the important plasma scales? And this is where I'm wrapping up. We talked about the gyro radii, and there it is for you. It has this perpendicular velocity, mass, charge, and the magnetic field. And so as I move in a magnetosphere, so from the magnetotail lobe into the inner magnetosphere, just the dipole component of the Earth's field is going to change. Changes as 1 over r cubed. And so my particle dynamics are going to be different in the tail than in the inner magnetosphere because scale sizes have changed. Another one that you'll see a lot is this inertial length, this C over the plasma frequency. And so you could have a C over omega pi for the ions or omega CE for the electrons. And that gives you a sense of the scale at which you are no longer frozen into the field. So suddenly this frozen influx condition is violated. So that's important for reconnection, is finding out where that happens. And here's just a whole bunch of other ones you can think of: Debye lengths, skin depths in terms of electromagnetic radiation or plasma waves, bounce scales, drift scales, right? All of them have spatial and temporal things, and depending on the problem, you need to keep up with what they are. So what you'll hear later today is what reconnection actually does. And I mentioned these two things already: the conversion of magnetic energy to the kinetic and thermal energy, and also this change in topology. I'm connecting one flux tube to another. So I can take what's on one flux tube and put it into another. So that's where I can get the exchange of mass and conversion of energy. So that's why reconnection is so fundamental. So the flux tubes are the quanta of the plasma universe, and they just never interact. They're just be flying around. But if I want dynamics, if I want to see something change, I need to get that interaction. And reconnection is the process that does it. And I've already shown you this Dungy cycle, taking the magnetic energy and the solar wind dynamic energy and the thermal energy and putting it into the magnetosphere. And when you do that, that's when you get the storms and substorms. And so if you're studying magnetosphere physics, you're usually studying storms or substorms, some component of it, how they create waves, how they energize particles, how they create aurora, and with the space weather applications increasing, how those impacts impact us. How does it impact my GPS navigation for airlines or whatnot? And just to finish up with magnetic energy, one of the things we don't think about in this heuristic, what is energy? You know who discovered energy? Who was the greatest scientist ever that discovered energy? He looked under a rock. Yeah, right. I mean, who knows, right? I mean, it's a made-up concept. It does really good, though, explaining all the natural world about us. And once we figured out this principle of conservation of energy, it made life simple for all types of mechanics problems. But it's just this thing, like a magnetic field line that we've created to help organize our thoughts. And so one made-up thing, these magnetic fields that we don't see are invisible, has impact because it has energy. There's an energy density. And one of the weird things, if you look at the energy density, b squared over 2 mu naught, that has the same units of magnetic pressure. And so one of the things, that just as an aside, I want you to verify that the units of energy density has the same units as pressure. So we normally don't think of energy per volume, but what does energy density mean? Because that will come up a lot. And so here's all of these timescales. So the take-home message from this morning, 3 universal constructs that are self-similar. So it doesn't matter where you look, they look the same, but they can have very different scales depending on the background and internal origin of the plasma and magnetic field. Cavities, current sheets, and flux tubes. Flux tubes are these fundamental units. You can sort of think of the entire plasma universe as these rubber bands that are able to move around. They can't cross each other. So if they come up against an object like a magnetosphere or a comet or a dust particle, they're going to get bent, or there's going to be some type of interaction. There's going to be a current sheet that forms. And this process of magnetic reconnection then can couple it, can allow rapid diffusion of that field through the object. We can talk about slower diffusion in planetary objects that don't have atmospheres and magnetospheres. So if you want to understand the heliosphere, so what you're going to hear pretty much throughout the rest of this week is reconnection. That's why NASA is investing $1.2 billion on MMS. Right? It's one of the key ideas. And reconnection is complicated, and why we don't have yet really good ideas on how to predict or forecast a lot of the dynamics is we don't have the ability yet to figure out what are the global configurations that influence the electron scale dimensions that would then drive reconnection at that point and not that point, or why it turns off, or why it turns on, or whatnot. So as we develop the physical intuition, we'll have a better way of predicting the next geomagnetic storm or what's going to happen on the sun. So I think we have introductions now. Is that right, Nick? Introductions now or break? Okay. But okay, but before we take a break, just a few minutes, would like you to ask me one question, and if you don't, I have the list of names, and I'll ask you a question. What, Fred? Yeah. Cool.
Do those show evidence of magnetic structure? I thought those were fairly hydrodynamic.
Yeah, so it's an astrophysics model, right? As everything's hydrodynamic. So how do I measure the magnetic field of the sun? Or how do I know that there's a magnetic field in interstellar space? So I have for like the sun, I'm going to do spectroscopy, and the Nobel Prize was given to Zeeman and his advisor for recognizing that emission lines split in the presence of a magnetic field, and that separation is proportional to the strength of the magnetic field along the line of sight. So we can make maps of the line of sight magnetic field. There's also, if I have an electromagnetic wave propagating through a magnetized plasma, I can get Faraday rotation, I can get the polarization of that field, and so I can measure what that intensity, but it's complicated. It's a line of sight integral, and it has this B and N in it, so it gives me something about density. So, but I can infer remotely what the magnetic field is, but almost all of them are line of sight, and they usually give me a component, and I'm looking. So how would I infer a 3D magnetic field structure of an astrophysical object?
You also measure cyclotron and radio?
Yep, so we knew more about the Jovian magnetosphere before we went there through synchrotron radiation. Essentially, you know it was a radio source in the sky, so you say, how do I make radio waves? And so if I have an energetic electron propagating down a strong magnetic field, I'm going to get synchrotron emission. And so from looking at the radio emission, I can tell you what the field strength of Jupiter is without measuring it in situ, right? So I could be looking for radio waves, or how else would I infer 3D magnetic field structure? So that tells me it's a magnetosphere, because I have to have things trapped, spiraling down. Yep, so for a spacecraft, if I can send a spacecraft, so how can I can measure structure by sending a spacecraft. right? And so that's the NASA divides everything into 4 components in SMD, the Science Mission Directorate. There's astrophysicists, they study everything outside the solar system. There's space physicists, everything inside the solar system. Earth science, who study everything to do with Earth, and planetary science on the surface structures of the planets. But the big difference between astrophysics and space physics is we build things to measure things in situ. We can go there. Astronomers build different telescopes to look at different frequencies. Is there any, can I see a magnetic field? I can see the effects of it. I mean, if I had as I mentioned in here, if I had a electron beam and I fired it into a plasma chamber with a magnetic field, let's say that's perpendicular to my beam, what's the electron going to do? They're going to get deflected, right? And if I have it so I'm in a plasma that lights up, that glows when it gets like a solar prominence or a fluorescent light bulb or whatever, I would see that path of the beam, right? So we can look for things that look ordered but it's really hard to figure it out. And often what you do is you first try the hydrodynamic model, and if it does it, good. And then when you start looking at knots and dynamics, that's when you often say, okay, I need to go to MHD. I need to figure out that it looks like the tail disconnects occasionally, so I need to have reconnection going across it. So, but great. So, as the scientist that's trying to figure out structure and dynamics, we have to see it. Most of the things that we deal with, we can't see. So we have to figure out how what we were interested in actually impacts something we can see. And so that's always the next step. And so if you really want to make a name for yourself, try to find a way we can see something better. If you could figure out Zeeman glasses, where you could see the 3-dimensional structure of the magnetic field, Nobel, and you would be buried knighted in Westminster Abbey, right? I mean, but order of magnitude is also the other thing. If I can make the same measurement, but at an order of magnitude better resolution, order of magnitude less mass, less cost, that's how you do it. So when you're thinking of what you want to do for your PhD project or as a career, is there a way that I can do something about an order of magnitude better than what we do now? And that's the big leaps. Yeah, so the moon is generally neglected, though it's not. So obviously, if I'm studying the atmosphere of the Earth and the ionosphere, thermosphere, the tidal effects have a big influence on the dynamics on diurnal and longer timescales. So I need to figure out the gravitational effects, the tidal forces on the Earth. But in terms of plasma physics, the moon doesn't have a thick atmosphere. It's called really an exosphere because all of the ions and neutrals are due to collisions or photo impacts with the regolith. And so it has a lot of potassium and sodium and all types of things that get knocked up. Once those neutrals get knocked up, they can be ionized either through impact ionization or ultraviolet, and then they become ionized. And so then you start getting this pickup effect around the moon. And there's a number of NASA missions that have been looking at it. You can observe it from sodium is cool because sodium vapor lights, it emits in the visible, so you can actually observe the exosphere of the moon at first and third quarter, it has this comet-like feature. But in terms of mass, momentum, or plasma, it has very little effect. ICE, International Sun-Earth Explorer, and AMPTY, the CCE, the Charge Composition Explorer, had the capability of actually measuring lunar ions in the Earth's plasma sheet. So 2 or 3 days a month, the moon is inside the magnetosphere as it goes around the Earth. And so then we have plasma sheet ions hitting the surface that can knock them up, and they were able to measure potassium and sodium ions. So we know It contributes, but it's a really small fraction. The mass of the satellites in orbit around Earth are much greater than the mass of all the plasma in the Earth's magnetosphere. There's just not a lot of stuff. So for the outer planets, you can have other sources that moons become important. And in Jupiter, Io is king. It dumps tons of plasma that gets ionized and controls a lot of the dynamics. When we talked about Saturn, not only are the rings very close, but Enceladus has geysers of water, and it's the dominant source of most of the plasma in the Saturnian magnetosphere, these water geysers coming out. And so different magnetospheres, different cavities, the size of it and its dynamics is going to depend on the source of the magnetic field, intrinsic or not, and the source of the plasma. So if I have a volcano or a geyser or something that can kick out a lot, it's going to be very different than if I'm a moonless magnetosphere. But those are the questions you're always asking. Why is it different? So good. So I'm thinking this anywhere, but yeah. So there are ways to measure vector magnetic fields, but often they take time or approximations because you're generally measuring a line of sight. Yeah. So what SDO? How often do you get a vector magnetogram map source surface? Is it a few minutes now? Okay. And they now are developing abilities to measure from different lines. So you can start seeing what the field is, not only in the photosphere, but in the chromosphere. So you can start getting that structure. So, great. So Nick left. We have a break. And then introductions. And there was asked on Facebook about what the introductions involved. And so I hope all of you got that packet. We wanted you to come up. You have about 30 seconds to describe your PhD research. You get one slide. And I'm kidding. But if we can take a 10-minute break and come, or I guess 14-minute break and come back at 10:40, we won't be too behind schedule. And then start that student introduction. Yeah.